Good day, Sir Rigo Melares. I am Isabel B. Kinsey, and this is the presentation of Group 7 IT 100. Our topic is all about abstract algebra. What is abstract algebra? Abstract algebra usually means group theory. This is about sets of transformations that are associative, sometimes commutative, and a few other things. If math describes the universe, group theory is a wallet for it. Why is algebra so important? Algebra is an important life skill worth understanding well. It moves us beyond basic math and prepares us for statistics and calculus. And what is the purpose of abstract algebra? Abstract algebra is useful because it provides another way to look at the same problems of classical algebra that could always provide different insights to the same problems, but abstract or classical are all relative terms. After you're familiar with the concepts, abstract will become concrete too. Let's proceed to the fundamental concepts in abstract algebra. First is sets. A set is a collection of elements or numbers or objects represented within the curly brackets. For example, open bracket 1, 2, 3, 4, close bracket is a set of numbers. And next is binary operation. What is binary operation in algebra? In mathematics, a binary operation or dyadic operation is a calculation that combines two elements, called operands, to produce another element. More formally, a binary operation is an operation of arity 2. Examples of binary operation on the integers are addition, subtractions, and multiplication. Let's proceed to the identify elements. An element such as 0 in the set of all integers under addition or 1 in the set of positive integers under multiplication that leaves an element of the set to which it belongs unchanged when combined with it by a specified operation. An example of an identify element is 0 in the equation 5 plus 0 equals 5. The element of a set of numbers that when combined with another number in a particular operation leaves that number unchanged. For example, 0 is the identity element under addition for the real numbers. Since if a is any real number, a plus 0 equals 0 plus a equals a. And next is inverse elements. An inverse of an element is another element in the set that when combined on the right of the left through the operation, always gives the identity element as the result. For example, if E is the identity element, then E number E equals E. So by definition, when E acts on itself on the left or the right, it leaves itself unchanged and gives the identity element itself as the result. Let's proceed to the associativity. The associative property states that you can add or multiply regardless of how the numbers are grouped. By group, we mean how you use parentheses. In other words, if you are adding or multiplying, it does not matter where you put the parentheses. For example, open parentheses 75 plus 81, close parentheses plus 34 equals 156 plus 34 equals 190. And 75 plus open parentheses 81 plus 34 close parentheses equals 75 plus 115 equals 190. The sum of both sides is same 190. Next is commutativity. Addition and multiplication of real numbers are both commutative. That is, the order of the numbers does not affect the result. For example, 2 plus 3 equals 3 plus 2. In general, this becomes A asterisk B equals B asterisk A. Let's proceed to the definitions of some related terms. Axioms. As used in modern logic, an axiom is premise or starting point for reasoning. As used in mathematics, the term axiom is used in two related but distinguishable senses: logical axioms and non-logical axioms. Any axiom is a statement that serves as a starting point from which other statements are logically derived. For example, an axiom could be that A plus B equals B plus A for only two numbers A and B. Axioms are important to get right because all of mathematics rests on them. If there are too few axioms, you can prove very little, and mathematics would not be very interesting. Next is statement. In mathematics, a statement is a declarative sentence that is either true or false, but not both. A statement is sometimes called a proposition. To be a statement, a sentence must be true or false, and it cannot be both. Briefly, a mathematical statement is a sentence which is either true or false. It may be, for example, the square root of 4 is 5 is a mathematical statement, which is of course false. Let's proceed to the mathematical proof. A mathematical proof shows a statement to be true using definitions, theorems, and postulates. For examples, direct proof can be used to prove that the sum of two even integers is always even. Consider two even integers x and y. Since they are even, they can be written as x equals 2a and y equals 2b. Respectively, for integers a and b, then the sum x plus y equals 2a plus 2b equals 2. Open parenthesis a plus b close parenthesis. Next is hypothesis and conclusion. The hypothesis of a conditional statement is the phrase immediately following the word if. The conclusion of a conditional statement is the phrase immediately following the word then. Hypothesis, two lines from right angles, and conclusion, the lines are perpendicular. Next is proposition, is a statement that is either true or false but not both. Example, Kizara bought a new car. June has 31 days. And let's proceed to the connectives and compound processions. Compound procession is a proposition that involves the assembly of multiple statements. Connective is also called sentential connective or propositional connective in logic, a word or group of words that joins two or more propositions together to form a connective proposition. Let's proceed to the equivalent statements. Are statements that are written differently but hold the same logical equivalence. Examples, if you do not clean your room, then you cannot watch TV. You clean your room or you cannot watch TV. And next is negating quantified statements. The negation of a statement about all. Object is not all. Not all can often be expressed by some are not. Examples, some snowflakes are the same. No snowflakes are the same.
I am Erwin Jr. S. Patalingog from BSIT 1A, and I am going to present to you the review on set theory. Please lend me your ears as I am discussing to you the different types of sets, theories, and its uses. So what is a set? Set is a well-defined finite or infinite collection of things, objects, or ideas. It is said that members of a set are often referred to as elements, and the notation E is used to denote them. Example, if an object X is an element of set A, we write this equation. If an object X is not an element of a set A, we write this equation. Notation is the list of each element separated by a comma, and then put some curly brackets around the whole thing. Symbol N means and or intersection. U means or union. Null means set containing no elements called the empty. Set bracket called set bracket or braces. Examples, socks, shoes, watches, shirt. Index, middle, ring, pinky. The three dots are called an ellipsis and mean continue on infinity. Define a set. 1. Listing the elements. Number 2. Describing the elements. This is read as C is the set of elements X such as that X is an integer greater than minus 3. Numerical sets. Set of even numbers. Set of prime numbers 2, 3, 5, 6, 11, 13, 17, and so on. Properties of sets. finite sets and infinite set. Finite sets are sets that have finite numbers of numbers. Meanwhile, infinite set is a set which is not finite. It is not possible to explicitly list out all the elements of an infinite set. Example, T equals to X, such as X is a triangle. N is the set of unnatural numbers. The null or empty set, null set does not contain any elements at all. It represented by the symbol bracket or null. Set quality. When one or more sets contain exactly the same number of members or elements. Subset. If every element of a set B is also a member of a set A, then we say B is a subset of A. We use the same symbol C to mean it's a subset of, and the symbol null to mean it's not a subset of. B. Universal set. Set of all elements under consideration denoted by capital U or sometimes capital A. What is Venn-Euler diagram? Euler diagram is a picture that represents sets and their relationships consist of closed curves. The elements of which are represented by the interior of the curves. Venn diagram. It represents all possible overlap permutation between sets.
Hi, good morning sir. I am Joshua Tinga Pasturan, BSIT 1A. First topic, mathematical reasoning is the critical skill that enables a student to make use of all other mathematical skills. Mathematical reasoning are able to reflect on solution to problem and determine whether or not they make sense. They appreciate the previous use to power of reasoning of a part of mathematical. My next topic, kinds of reasoning. There are 4 types of reasoning. Number 1, deductive reasoning is the type of reasoning that uses formal logic and observation to prove the theory or hypothesis. In deductive reasoning, you start with an hypothesis and then make observation or deductional thought to validate or refute the supposition. You can use deductive reasoning to apply a general law to a specific case or test in deduction. The result of deductive reasoning typically have a logical certainty. Number 2, in deductive reasoning, use theories and supposition to evaluate observation. In some ways, the opposite of deductive reasoning as it involves reasoning from a specific case to devise a general rule. The result of deductive reasoning are not always certain because it uses conclusion from observation to make generalization inductive and part to whole argument. Number 3, analogical reasoning. Similarities between two or more things and then use those characteristics to find another qualities common to them. It's based on the brain tendency to notice pattern and make association. Once the brain recognizes a pattern, it can associate the pattern with specific things, and this lead to analogous reasoning. Analogous thinking can help you expand your understanding by looking for similarities between different things. Number 4, adaptive reasoning is a type of reasoning that uses an observed or set of observation to reach a logical conclusion. It's similar to inductive reasoning. However, inductive reasoning permits making best guess to arrive at the simple conclusion. Inductive has application in troubleshooting and decision making, especially when dealing with constituents. Adaptive reasoning is especially useful when explaining an observation has very little or no existing knowledge about the conclusion of adaptive reasoning may not always be current and may require reviewed verification. Definition of logic. Logic can include the act of reasoning by human in order to form an opinion as well as classification and judgment from some forms of logic can also be performed by executives and even animals. There are two types of logic. Number one, symbolic logic. It deals with how symbols relate to each other. It assigns a symbol to variable reasoning in order to be able to check the veracity of the system through a mathematical process. You typically see this type of logic used in calculus. Symbol logic sample. Proposition: if all mammals feed their babies milk from the mother, hypothesis A practices. If all cats feed their mother's milk. In the case of B, hypothesis all cats are mammals. Hypothesis C practices what A means and the symbol means increase. Examination proposition A and proposition B lead to the conclusion C. If all mammals feed their babies milk from the mother and all cats feed their babies mother's milk, it implies all cats are mammals. Number 2. Mathematical logic. In mathematical logic, you apply formal logic to math. This type of logic is part of the best for the logic and symbolic logic are often used interchangeably. That's all. Thank you.
Go D everyone! I am Jelani A. Tabaliha, BSIT 1A. I'm going to present now the report that assigned to me. It's all about mathematical proofs. What is a mathematical proof? A mathematical proof is an inferential for a mathematical statement showing that the stated assumption logically guaranteed the conclusion. Let's proceed to the concept and definition. A mathematical system consists of assumed, definition, and undefined terms. An assumption is assumed true. Definitions are used to create new concepts and terms of existing one. Undefined terms are only defined implicitly defined by another assumption. Within a mathematical system, we can derive theorems. A theorem is a proposition that has been proven true. A lemma is a special kind of theorem that is not usually interesting. A corollary is a theorem that follows quickly from another theorem. Euclidean geometry is an example of a mathematical system. Deductive reasoning. The process of drawing a conclusion from a sequence of propositions is called deductive reasoning. Example of deductive reasoning. Acute angles are less than 90 degrees. This angle is 40 degrees. It must be an acute angle. A is equal to B. B is also equal to C. Valid argument. The proposition P1, P2, Pn are called the premises or the hypothesis and Q is called the conclusion. The argument is valid provided that if P1 and P2 and Pn are all true, then Q must all be true. Otherwise, the argument is invalid and fallacy. There's a form of argument. If P1 and P2 and Pn, then Q can be written as a sequence of proposition. Example of valid argument. All cats are mammals and a tiger is a cat. So tiger is a mammal is a valid deductive argument. Rules of inference for proposition. For a proof as a whole to be valid, each tip of the proof has a drawn intermediate conclusion that are valid. To make sure that intermediate conclusions are valid, each conclusion has to be deduced using some of the rules of inference. See table next slides. There are 7 rules of inference: modus ponens, modus tollens, addition, simplification, conjunction, hypothetical syllogism, disconjunctive syllogism. Example of rules inference. Modus ponens. If today is Saturday, then J will go to work. Today is Saturday. Another. If A is true, then B is true. A is true. Example of inference modus tollens. If A is true, then B is true. Another. All fish have scales. The salmon is a fish. Therefore, the salmon has scales. Example of rule of inference addition. I study hard, therefore I study hard, or I will get rich. Example of simplification. I study hard, I get A, therefore I study hard. Example of rules inference conjunction. One cannot be wealthy and poor at the same time, but you are wealthy, therefore you are not poor. Example of rules inference disconjunctive syllogism. Either my pet is a dog or my pet is a cat. Example of rule inference hypothetical syllogism. If I don't wake up, I cannot go to work. If I cannot go to work, then I will not get paid. Rules of inference and quantified statement. There are 4 rules of inference and quantified statement. Let X be a universal quantified variable in the domain of discourse D, such as P quantity X is true. For all X, therefore D P quantity X is true. This is the 4 rules quantified statement. First rule of inference, universal instantation. For all X belong D, P quantity X. Therefore, P quantity D if D belongs D. Second rules of inference, universal generalization. P quantity D for any D belong D. For all X belong D, P quantity X. Third rule of inference, extension instantation. Exists X belong D, P quantity X. Therefore, P quantity D for someone D belong to D. The last one is the rules of inference existential generalization. P quantity D for some D belong to D. Exist X belong to D, P quantity X. That is a 4 rules of inference in quantified statement. So which rule of inference or quantified statement is used in the following arguments? The student taking CS 1 through 4 lab proofs. Let's D be the domain for all students taking CS 1 through 4. Let's Q denote the proportion X lab proofs. We can rewrite this as exist X belong to D, X quantity X. This means that we can find at least one student D in CS 1 to 4 which Q quantity D is true. Conversely, if we can find at least one student D in CS 1 to 4 for which Q quantity D is true, exist X belong to D, Q quantity X is true. The last one is the combining professional and quantified statement inference. Show the conclusion Len lab Unix follow from the hypothesis. First hypothesis, everyone love either MS, DOS, or Unix. Second, Len does not love MS, DOS. Let P quantity X denote the proportional function X lab MS, DOS. Let Q quantity X denote the proportional function X lab Unix. The first hypothesis can be written as for all X, P quantity X or P quantity X. By universal instantation, we have P quantity lane or Q quantity lane. The second hypothesis is not P quantity lane or Q quantity lane, not P quantity lane. Q quantity lane by disconjunctive syllogism, therefore the conclusion follow from the hypothesis. That's all for my part about mathematical proofs.
Today we are going to work on truth tables, and this can be found in short discrete mathematics or logic types. If we and then the negation of P and Q, so how to start our truth tables by writing a column. First, we need to write a column, copy a P, then a Q, write down a Q here. And then copy that. And then we have P and Q. Copy the P and Q. And then copy the negation of P and Q. And then copy the whole example. P if P and then the negation of P and Q. How to start our first column? Right. True, false, false. And the second column, the Q, right. True, false, false. Here on P and Q, what they're saying is they want true both P and Q columns. So true and true is true. True and false, Q is a false, so false. False and true, not all true, true. False and false, so false. So anytime we have this negation symbol, it's going to be the exact opposite of what is what in the front of basically the P and Q and not P and Q. Anytime you have this negation symbol, it's going to be the exact opposite of what is here. The example: false, true, and true. Okay, we get if P and not P and Q column. Two different columns. We get the P here, P column, which is the first one. So we have a look now. What you do is to look at the arrow. Look at the arrow. What the arrow is pointing to. If that is true, then it doesn't matter what the other side says. So it's going to be true. Okay, and this is true, and false. It's gonna be false. Okay, takes a little bit of getting used to, but once you memorize that, then you'll have no problem with it.